Good afternoon. Thanks for coming, guys. So I am Jags Ramnarayan. I work in the GemFire, essentially the fast data group, if you may, within Pivotal. Well, I don't know what I do. I do a lot of meetings. And then I'm a sales guy masquerading as a developer. So that's what I do. So Anthony, here, you want to just say a few words about yourself?
Hi, I'm Anthony Baker. I work with Jags up in Portland, and I'm an engineer on our GemFire and SQLfire products we'll be going into today. So I'll let Jags tell you more about what we're talking about today.
All right. So I guess I don't know how many of you attended the talk from Adam this morning, giving you an overview of Hadoop. So a lot of you know that Hadoop is really great for our volume, write scalability. Massive volumes really well, but clearly it's not really designed for anything real time, right? When it comes to online systems, when I have thousands of concurrent users, I need predictable latencies, it's really not the design center. So what we are really looking at is how do you take an in-memory data grid, right? A very fairly sophisticated distributed caching platform, blend it essentially with a very rich, if you may, coupling. And that's really what we're going to focus on today, that what that coupling means, how do we now get take Hadoop, the best of Hadoop, which is the volume scale, and the best of what an in-memory data grid does, which is its applicability from a scale standpoint for concurrency for online applications, bring it together, and hopefully we realize the best of two worlds, right? So we're going to cover a lot of this thing from the context which we come from, which is GemFire and SQLfire, and then the Pivotal Hadoop thing. But hopefully you'll see a lot of these interesting patterns there. So with that, here's a quick snapshot of the agenda, just so that we can remain on track here. So I'll touch on the in-memory data grid essentially from a GemFire perspective. How many here are familiar with GemFire? Bunch of guys. How many here are generally familiar with just any in-memory data grid, NoSQL, Cassandra, things like that? So good. A lot of you do. And how many here generally have awareness of Hadoop in general? Okay, cool. Excellent. Yeah, so the thing is here, we're not going to go walk through all the concepts here. We assume some level of awareness. We'll brush through some of these things. So that's what I'll do. I'll just cover sort of these general capabilities in in-memory data grid, what the strengths and weaknesses are. And we look at the weaknesses, then we look at essentially, there's a core of Hadoop, HDFS, its weaknesses. And then we talk about our proposal. From there, we go into looking at a demo, looking at our SQL syntax extensions. We specifically go into our HDFS integration architecture. We do a demo there. And then hopefully if time permits, we'll do also talk about Map-reduce and how we integrate into that Map-reduce framework really well. And then if time permits, we'll get into sort of, what we call as the in-memory stored procedures. So we'll get into some of those concepts also. And again, if time permits, we'll get into edge-based comparisons. So that being said, here is a slide that has no relevance to this talk, but it's more of my state of mind, right? So, I don't know how many of you are looking at all these NoSQL, new SQL, all sorts of, next generation like databases, they're just pouring in, right? It's like a deluge. And for me, I'm still having fun, right? And I empathize with people who are really trying to say, hey, how do we now look at all this stuff, distill it so that we can make sense out of it, use it for our apps, right? So in general, when we look at sort of this next generation databases, we have a firm belief that a lot of these core concepts and how we essentially look at in-memory database is shifting towards a model that is fundamentally memory driven, its distribution as its core, the ability to say that, hey, if I have a set of machines in which my database is running, I can elastically grow or shrink it, which is an extremely difficult problem to solve, especially when you're dealing with data, when you land up having to move massive quantities of data. HA, the aspects of high availability is very rooted in this thinking, right? So, and you have a whole ton of in-memory data grids, that sort of thing. And of course, when you start thinking about the OLAP database, which is the data warehousing class of products, we believe that, hey, the center of that gravity in some sense is slowly shifting towards the core of Hadoop, which is HDFS. But that being said, a lot of analysts talking about volume, variety, stuff like that. I think it's simply a cost per terabyte that's putting the pressure and everything is coming down. So what is an in-memory data grid? At the core of it, it's nothing but it's a fairly sophisticated distributed cache, a distributed key value store in some sense, where I can pool the memory across a bunch of machines. Essentially, most of them manage objects really well. Like if you look at our solution, whether it's Oracle Coherence, Gigaspace, several of them, it's all about taking Java objects, spreading it across a whole bunch of machines, supporting a variety of serialization formats and models so that I can get interoperability with other languages in a very native way. We also support SQL, and a lot of the in-memory data grids do, right? I mean, it's also about saying querying. It's not just about raw keys and values, which are blobs. It's also being able to understand the structure, so I can essentially index on it in memory and essentially run distributed queries on that too, right? So that's fairly important. Transactions are natively supported in most of the products. There are different storage models, right, which is sort of one of those nice things compared to some of these NoSQL products that says, hey, when I start looking at star schemas, quite often you'll end up looking at, chunks of your data model that are slow changing, reference data code tables that have what have you. And it makes a lot of sense to simply have them as replicated tables, right, or simply replicas that are spread across the grid. And then you take your fact tables and you spread it across your grid. And the beauty of that is now, when you get a query that is doing a join, I can simply prune it to a small number of nodes, execute the query a lot faster, and you avoid unnecessary pipeline joins across your grid, right? So, and that's one of the ways by which, we cater to sort of this low latency world really well, right? Saying, hey, if I get, 1,000 concurrent guys all hitting queries, if I can prune those guys to just specific set of nodes, I can spread the load across many machines. I can essentially dramatically scale. All the in-memory data grids, unlike if you look at a Cassandra, we simply, when it comes to HA, it's all about synchronous copies in the grid, inside the grid, and then you can make asynchronous copies outside the grid over the WAN. But by making synchronous copies in the grid, you can essentially give read scalability so that if any queries are coming in or reads are coming in, if I can guarantee consistency of those copies, I can spread across the copies, right? And most of us do some sort of overflow to disk, or essentially allow some pluggability into a relational database so they can store it. Everybody supports, most of these products are Java driven, so on the server side, so which is nice, right? And we get this common thing where people are running essentially this thing alongside a Spring container. So you start up essentially either GemFire or SQL servers, you can run inside or alongside a Spring container. So you can essentially, when deploying any Java code, like for instance, the stored procedure model we support, you can simply have it driven off of Spring annotations or Spring data. Other key aspect is support for multiple failure detection models. The ability to sense, detect, and respond to failures is absolutely critical in a clustered system. And for a real-time system, as I'll talk more later on, how critical it is absolutely key, right? And that's where sort of HDFS falls apart a little bit. So the ability to support multiple failure detection models is key, and of course, distributed consensus, how you do membership management, how you essentially allow this elasticity to happen with consistency in mind is absolutely key. A lot of the vendors differentiate on, like for instance, we differentiate ourselves with SQL support, the ability to do WAN replication, having a very native event-driven publish-subscribe model is absolutely key, right? So with the in-memory data grid, the key pattern is distributed caching, right? And there you have, support for what's called as read-through, which is, hey, I'm looking for a piece of data, it's not there, go look for it in the database, fetch it, get into the cache, and then release the object, right? Release the request. Write-through, which is, hey, if I'm making changes, I want to transactionally make sure that those changes are reflected in the database before I essentially commit it inside the grid itself. And right behind, which is all about saying I can get reliable sort of enqueuing of all the changes that are happening, and I can take these batches and essentially persist it inside the database, right? So which is really pretty common patterns, but there are challenges, especially for some very write-heavy, sustained write sort of applications, and they're obvious, right? I mean, with synchronous write-through, I mean, you're only going to go as fast as the database is going to allow. So if you have too many writers coming in, they're all going to bottleneck potential in the database, right? Pretty straightforward. And the other problem is, if you're doing essentially a write in a transactional consistent manner, you got to go through an expensive two-phase commit protocol to essentially make sure that the database and the cache essentially reflects the exact same consistent state. With asynchronous write behind, which is the ability to enqueue, it works great, but up to a point, right? But because if your loads are always sustained write-heavy loads, then at some point, if you're continuing to flush these batches, maybe that also doesn't keep up writing to the database. The moment that happens, I mean, your queue is going to fill up, and you're ultimately going to throttle the writer, right? So again, asynchronous right behind a great model, it only works to a point. And the reason is that you essentially, if you have a cluster of, let's say, 50 nodes, they're all converging and writing to a single central database, you can only go so much, even at the database scales, only go so much on the network, right? But the more important, perhaps, point is, from what we have observed, is parallel recovery, right? I mean, when two or more nodes of your cluster go down, if let's say your hash partition, you don't know what portions of data is lost, and unfortunately, potentially have to bounce the cluster back up again, especially if you're provisioning all the data inside memory. And when that happens, and let's say you have a few terabytes of data, getting those few terabytes from the database back into memory can be an extremely complex task. Not only that, your database probably was used by a whole bunch of other applications, and you're going to get this huge sporadic burst of load, which most likely the DBAs are not going to tolerate. Again, the parallel recovery is the same challenge even with this sort of design. Some in-memory data grids like GemFire offer shared nothing persistence, which is that each partition node essentially persists to local disk without anything shared between the disk architectures, right? And I mean, it's pretty fast because as these writes happen, you're constantly appending to these log files, right? And you're just streaming all your writes into these log files, so there is no seeking going on disk. And in theory, if you take 10 machines, you can essentially write the equivalent of the transfer rates multiplied by 10 across those machines, right? So you can get pretty high throughput. But the problem with that approach still is that if your data volumes are pretty high and your cluster were to be bounced again, you still have this problem of saying, hey, how do I now scan all my logs and recover my data sets and recover my indexes back into memory, right? So again, you have a problem of saying, if I were to ever bounce, there's a recovery time delay, that's a problem. So on the Hadoop side, where do we stand, right? So Hadoop, I mean, from our standpoint, it's absolutely great because from the core Hadoop, from the HDFS standpoint, it's maturing very rapidly. That's one big plus point for us. And again, I mean, when it comes down to managing a few hundred terabytes of data, having something that's pretty rock solid is so fundamental, right? I mean, it's going to take, in my view, maybe 200 man years before something becomes absolutely rock solid. But we think that it's going to mature pretty rapidly. It's going to get ubiquitous. So the dependence on HDFS is a bet like we want to make, right? And of course, the other thing is that the core design center, a very simple coherency model, a model that basically has baked into it, HA, right? As you guys know, I mean, you write into a block in Hadoop, you get 3 free replicas out of the box, and the name node is able to sort of say, hey, if something were to go wrong, how I can recover back. So all that stuff at the core HDFS level is something we really want to bank on, right? Several other advantages, right? For instance, I mean, we see that many of the storage systems that are coming out there, like for instance, what EMC produces, the Isilon, they also are wrapping their storage machinery with just an HDFS interface, right? So essentially, it becomes a very ubiquitous way of storing. Today all the conversations and talks are all about saying, hey, how do I take log information and dump it into Hadoop? How do I take essentially yet to be structured data, put it into HDFS, and then run massive sequential programs to structure it? But we think that we can see ways by which all sorts of content, including what you would look at from a standard SQL use in an online application, even that data can make its way into HDFS, very fundamental, and we think that's going to happen. Optimizations from virtual machines, just a growing ecosystem, right? An amazing growing ecosystem we want to depend on. So the design center for Hadoop, so where is the problem, right? I mean, the design center for HDFS is all batch and sequential, and I think those of you who attended, I mean, I don't know how many of you know this, but I mean, the smallest unit in Hadoop is a 64 megabyte block size, right? And once the block is created, it's immutable. You can't really change it, even though now they have, files can be open and you can append. But the design center was such that, created once, create huge things, don't change it. And in fact, those are just those two principles that is, in my view, is the magic of Hadoop, right? Because it's like saying, in our world, I mean, at the end of the day, the challenge all comes down to how do you do the metadata management, how do you do the locking and consistency management when you have replicas going. But the nice thing in Hadoop is that each object is a 64 megabyte big chunk, right? So the metadata management makes it so simple. It's like saying, if I have 10,000 of these objects, I got what? I mean, half a terabyte of real data with just 10,000 objects, right? So it's a lot simpler, and that's what really allows it to really scale really well. Now, that being said, I mean, many challenges, right? First is, there is no notion of saying, well, I want to look for a random record anywhere. So if you want to do a random record lookup, you got to sequentially walk through your block, find your record, return it back, and every single time you have to do that repeatedly. So again, it's not really wasn't designed for that. It's a write once, read many design. There are several other points about name nodes being a contention point. It's being resolved right now with HDFS 2.0. So I'll leave that aside, but the other big problem, I think, is the failure detection model, right? So anytime, let's say you have, I mean, everybody knows data nodes, name nodes, that sort of thing, yeah? So anytime you have a data node essentially not responding, maybe it failed actually, the clustering in Hadoop naturally tilts itself to thinking that, hey, it's an overload problem, not necessarily a failure problem, right? So you could easily get into situations, I mean, of course, there are knobs you can turn it down, but it's not really designed like that, right? Where, if a data node is unresponsive, before Hadoop marks that node to be dead, it could actually be minutes, right? In a lot of situations. And that's not going to work for your real-time app, right? I mean, you could easily have a situation where, imagine, your connections and your live things are going on a block that is now essentially not available, and you're all of a sudden blocked for like, several minutes, right? So those are those interesting problems when you start thinking about it, its applicability to real time becomes an interesting challenge, right? So what's our proposal here? The core of it is, just taking the in-memory data grid and at an each. So if you look at the in-memory data grid, it's really nothing but, you're taking a bunch of machines and it's all a whole bunch of partitions that you're managing as if it's a single cluster. We want each partition to be able to sort of completely parallelly write to HDFS and support multiple models. One is to say, hey, when changes happen, I can stream those changes into HDFS so that I have this, all the history and all the change records inside HDFS. But the more important thing is really trying to support read-write models. So this is where it starts to overlap heavily with what HBase is, right? I mean, how many of you know HBase? Few of you, right? So in some sense, think about it as we are taking the guts of, if you may, HBase. And to me, the guts of HBase is really its ability to manage extremely large volumes and give you random read-write capabilities, right? I can just write 10 billion records and start to look for just one little record inside those 10 billion records. And in reasonable lookup time, it can essentially fetch that record out back, right? So it's the same sort of core H file and that kind of design is what we're incorporating. And we're incorporating into essentially a data grid that's going to support SQL for online systems. You can do joins and you can do transactions and a whole variety of other things. And you're sort of blending it together in some sense. That's the general idea. So we think that data will be in many different shapes. So we want to support multiple data models inside this thing. SQL and objects and JSON, that's kind of how we're thinking about it. One other important thing is we think of operational data as a very first-class focus for a product like this. So in other words, you could have a situation where, hey, my data is actually 50 terabytes. But if you start thinking about online systems, I mean, what, 90, maybe 99% of the systems, 1 terabyte is good enough, right? I mean, 90 to 95% of all my requests can be met with that 1 terabyte data, right? My now data, my operation set, my working set data. So the idea here, unlike a typical database, we want to give you very explicit control over this operational set. So you can actually define in your table definitions that says, here is what defines my operational set, and we would guarantee that that operational set, in fact, will be in memory. So it's a little bit different than how a typical database would work, where given a chunk of memory, I would do some sort of LRU managing the blocks. Here we will explicitly manage that. The idea behind that is that, hey, when it comes to rich querying and indexing and things like that, initially we'll support it completely on that online, if you may, that operational tier, giving you that extreme performance, right? But all writes as they happen will absolutely make its way into Hadoop, and it's all configurable at a table by table level. So essentially what you get is operational data, your now data, it's all in memory. All the data that you have created essentially is all in Hadoop, right? And the data can essentially be in many different shapes. We'll continue to support sort of different, essentially storage models, right? In memory local disk, you get replication, and of course, the ability to say, hey, the data is actually on HDFS. So, I mean, the other part I mentioned was the SQL engine part, right? I mean, it's pretty fundamental, which is one of the big things that HBase really lacks, right? How do I essentially do queries? Can I have any number of indexes is there a cost-based optimizer that can figure out what the right query execution plan can be, things like that, ability to support transactions, and retain essentially the ability to say, hey, if I'm making all these changes, transactionally consistent fashion, boom, it goes back into my database if I wanted to do that too. So flexibility is very key. The other absolutely important aspect is, as all these writes are happening into the Hadoop tier, we want to write it in such a fashion that a sequential walkthrough of that data is absolutely possible inside Hadoop without actually going back to the in-memory tier to ask for the records, right? I mean, if you look at Mongo or Cassandra, I mean, there are all sorts of, everybody is saying, yeah, there is a way to get into Hadoop, right? I mean, you can get your data into Hadoop or push the data from Hadoop back in. But we think that it's very fundamental that if I'm using this tier for my online applications and on the back end that same data is being analyzed on, you can create sporadic, huge loads, right? So you want that very clean separation of saying what happens in the online operational layer is different than what can happen in terms of load and CPU and resources from an analytics standpoint, right? So the idea here is the data arrives, it gets into HDFS, and when it gets into HDFS, I mean, you can't just write. I mean, there are lots of techniques where you do batch, buffer, sort, write it. But once it's there, it's in a format which allows us to essentially do sequential, walkthroughs. You can do map-reduce, you can do Hive queries on it, or of course get it into sort of our product like Hawk, so they can do deep scale analytics on that thing, right? And then finally, once I analyze it inside Hadoop, the results, let's say, of a map-reduce job can automatically make its way back into the online tier, essentially the in-memory tier, right? So if you may, the map-reduce can emit results back into the online tier. I'm off, huh? All right, so here is a little product promotion, right? So we're going to come out with this thing called GemFire XD. It's going to be SQLfire, if those of you know SQLfire 2.0 initially, and then we'll later on expose objects and JSON natively also. And you get all these sort of good stuff from what SQLfire and GemFire have built for the last decade or so. And initially, the release is going to be a service within PivotalHD, the Pivotal Hadoop distribution. And so you get, a whole variety of things around install, config, this command center, monitoring pieces. There are a few optimizations to Hadoop that has been done in PivotalHD, so all of that. So this gives you a little perspective. Today in the market, there's just a flurry of, these SQL on top of Hadoop kind of class of products emerging. The idea here is to, this kind of presents saying that, hey, here is where we fit in, right? So if you start thinking about the real-time sort of latency, everything is real-time nowadays, right? What is not real-time, right? You're out of the market if you're not real-time. So, but really the way I think about it is like, hey, there's a latency spectrum, and we fit in that machine milliseconds to human interaction, seconds latency, maybe in the interactive ports latency, but we're not about batch processing, right? So you're not targeting to say, hey, here I'm doing a 20-table join, I'm doing an aggregation on, 2 billion records, right? That's my class of queries. My class of queries are queries that says, here's a user ID, give me his orders, join it with line items, ship it back to me, right? And there are 1,000 concurrent users all hitting it. There could be some level of analytics in the real-time sort of perspective, but that's the focus. Several products, if you may, on sort of this notion of very, I would say, pure real-time on top of Hadoop, HBase obviously as part of the Hadoop ecosystem. I was drawn to this, drawn to Scale. It's a new startup. They have a database called Spire. Fairly interesting because they're also sort of positioning and pitching the same thing, which is, hey, how do I make Hadoop and the ability to scale with data more relevant to online, transactional applications, right? And then VoltDB is a pure memory-based database. So what are the design patterns here? Quickly, the ability to do streaming ingest, right? So I have unbounded event streams coming in. And you just want to get all that data into Hadoop. So that's, you could do Flume, you could just do a variety of things, right? What to us is much more interesting is that, well, while I'm ingesting, there is some level of processing that needs to happen. While I'm ingesting, I have to look up some reference data. While I'm ingesting, I have to write back into something else, right? So that ability to think about processing while I'm doing stream ingestion is very very fundamental, and those are the kinds of use cases we want to cater to. At the same time, you could have situations that says, hey, you know what, I want to keep my data all resident in memory, but at the same time, all interactions, all changes that happen to data, I want to capture it in Hadoop so I can do some sort of modeling with it, right? Or as an example, let's say I'm a financial trading application. I want to keep all my instruments and the prices, the latest prices, all in memory, few thousand records maybe, right? But every change to that price record, I want to immediately capture it as tick data into this massively growing thing inside Hadoop, right? So now I'm a tick database in some sense inside Hadoop. Or you could do all sorts of interesting things where you're just capturing, even in a traditional, let's say, a sales-driven app, you're just capturing all your orders, your line items, what have you inside in memory. But every change, every potential interaction, I want to essentially capture it. So that maybe I want to do auditing, I want to do some sort of trending, modeling, what have you, right? So that's one, which is really, if you look at this pattern, it's all about this one-way path. In other words, I'm making all these changes, and I'm constantly doing these writes into HDFS. But in this model, there is no such thing as being able to ad hoc read the data back in, right? It's just like what you can do with even with, for instance, with Spring XD. The next pattern is really what we're thinking about is a high-performance operations database, which is what I was talking about before. That hey, I have some chunk of data that's going to sit in the operational tier, and a huge chunk of history is going to essentially land up inside my HDFS tier. And I might have ad hoc requests coming in for this history, and then inside a query, I should be able to pull in sort of a very random record back in, right? So this is really that read-write scenario with a massive scale with Hadoop. So with that, let's get into a quick demo, yeah?
Yeah, great. Thanks, Jags.
All right, thanks.
Just a quick checkpoint. Any questions so far? How's everybody doing? Making sense? So what we're going to do now is go from the conceptual level down into more of a user level, and how does this actually manifest itself to a developer or an application? Sorry, go ahead.
I did have a quick question. So did I understand correctly that SQLfire 2.0 plus PivotalHD is going to give you HDFS as a persistence layer for SQLfire?
Well, is it going to be SQLfire? That's an interesting question. But let me just put it this way. I mean, the product management decision whether it's going to be something new, it's not clear. But if people who have SQLfire licenses, I think they'll be able to essentially get this, right? But we're going to probably launch it as something new, as a new service, really, essentially. So yes, I mean, when you as a developer look at the product, it's all going to look like SQLfire, and as you will see in the demo, at least initially. And then we'll add objects and JSON and all that is sort of coming. Yeah.
Okay. Great. So to start off with, we're going to take a look at how does it look like from an in-memory perspective. So we're going to use a little schema here showing some flights. And every time someone buys a seat or gets a refund for their ticket, we're going to update the flight availability table. Every time a flight lands, we'll update the flight history table, and we'll just record all this information. We're just using this as an example schema. So carrying on. So create table. This is how your DDL looks like in a relational database. And here's what it looks like under GemFire XD. So we have one table type for replicating that data on every node in your system. Writes happen consistently. Every node sees the same data. This is, like Jag said earlier, this is great for reference data that has isn't updated very often, but has high read traffic. Another interesting table type is partition table. So in this case, what we do is instead of having all the data on every node, we take a portion of that data and group it into a set of buckets. And so if you're familiar with consistent hashing, we identify a partitioning key, take a hash of that, and then all the data with that similar hash ends up in a common bucket. And by doing that, what we can do is spread the load across the cluster and gain additional throughput. So that works great when all of our data is either massive or we have high write throughput. Alongside that, we then have to make sure that data is redundant. So we're going to create redundant copies of those buckets and spread those across the cluster. And you can identify how much redundancy you want in your application. When this happens, you'll see that if a node goes down, one of those backup copies will then become the primary for owning the consistent copy of that data. Then we'll go off and create a new backup copy asynchronously so that we satisfy that redundancy constraint for your system. The other interesting point about partition tables is that oftentimes you're going to be fetching data that is related. So as Jags mentioned earlier, you have a customer, they have orders, those orders have line items, and you want to access that all at once. And in a partitioning scheme, if you don't co-locate that data on a single node, you're going to end up pretty much fetching from every node on your cluster. And that distributed join is really slow and will kill your performance when you're doing it at high volumes. So in this case, here's an example of co-locating flight availability with flights. We want to fetch those together. So that gives you great join performance. And the last little DDL snippet here is doing partitioning, or is doing a persistent table. So what we do here is every time we get an update, we write that to disk in an append-only format. That lets us, if a node goes down, we can bring it back up. It's got its own copy of the data already. It can resume automatically. We can bring the whole cluster down. We don't have to back it up with a relational database. We can have a backing store on local disk. OK, so now we're going to take a look at actually running a demo on this. So in this demo, I've got a virtual machine on my laptop running GemFire XD. We've got a couple different types of servers. We have a locator. That locator is used for discovery and management purposes. In this example, I've only got one, but in a cluster, you can have more than one of those. We have a couple different data hosts that are actually going to store the data in our tables. I'm going to run a SQL client using a JDBC URL against this cluster, and we'll see how it looks. So let's dive into that right now. Great. Perfect. Let's fix this. OK, so the first thing we can take a look at is this pulse. And although the resolution isn't super awesome, there's a cluster view of the system where we can see we've got a locator and a couple data nodes in our system. So it's a pretty small cluster, but that's what we've got going on. It's going to show you things like the amount of memory you have, statistics about reads and writes, GC, and we're not going to be able to see that in this view, but it's also going to show our disk bandwidth and throughput. All right, so that's one way to look at it. We're going to take a look at, boy, that's really big. All right, boy, I'm going to have to change. OK.
I think it's going to be the same problem. Yeah.
Yep. All right, so this is just that schema I was showing you earlier. We've got a partition table that's got collocation and redundancy. So I'm just going to go ahead and run this. Boy, I'm going to have to guess what's going on. Yeah, all right, let's try that again. Dang it. All right, so we're going to go in and change this font size.
Yeah, I think that's what you should do.
Yeah. All right, so we're just running the DDL statement. Now we're going to go off and we're going to load some data in that in our schema we just created. So a bunch of insert statements doing their thing. So once we've done that, we can go back to our pulse. take a look at our cluster. Looks like we need to go in and log in. And there's going to be a data view we can take a look at here. And anyway, so now we've got 12 regions created, identifying our tables. We've got a bunch of data we've put into the system. So that's going to show us what's going on. So now let's flip back, and we're going to actually do some real queries on this data. All right, so first of all, let's just do a simple select statement. Nothing fancy, but just to, actually we need to go in and do get our JDBC connection going, right? So now we can go in, do a simple select, and we get back a bunch of results, which again, we're not going to be able to see. Awesome. All right. Well, anyway, I guess what I wanted to show you is that we're just doing regular old SQL. It's nothing surprising here. Looks just like a database. Another thing we can do is we can take a look at the types of tables in our system by querying some values from our system tables. All right, we need to figure out how to make this work. Dang, man.
Yeah, I think you need to.
Wow.
Why don't you just go back to the command line and just execute that way, right?
Yeah, yeah. Let's just go back here.
Well.
Yeah, yeah. I got to go to the other one.
Okay.
All right.
That's okay. I mean, it is just showing, hey, the fact that you can see that the tables are replicated, partitioned, what the policies were there, right? I mean, it's just.
There we go. So we can use the command line utility, and you're going to be able to see the exact same thing here. So if I paste in that information, what I wanted to show you is you can see we have different types of partitions, different type data policies for those tables. We have partition tables, we have replicate tables, depending upon what kind of table definition we used. All right, so let's keep going. There's some other interesting things I wanted to have you look at. One of the things we can do is we have a built-in function, so we can group our, we can find out how many rows are in each node in the system. So let's take a look at what that looks like. If we paste that in, we're going to see that there's two groupings. We have two data hosts running right now. So that's all great, but what we want to do is actually run more data hosts. So adding another node to our system, let's go in and do that. So we're going to fire up another data server. We'll just copy this to our system. All right, so now we're starting up another data host. And what we're going to do is we're going to tell SQLfire, let's go ahead and connect. And now we're going to tell SQLfire to go ahead and spread that data around the rest of the system. So we're going to run a rebalance operation.
Yeah, I don't think it started. I don't see that. There was a conflict.
Yeah, okay. Yeah. All right, so we can go ahead and, what a rebalance operation is doing is as we add nodes to the system, it's going to look at the load and spread the data so that everyone has an equal amount of load. So a lot of interesting stuff you can take a look at, but just wanted to give you a flavor of how things work in the system. It's just a straight SQL database. You can do all sorts of queries, and we'll get into more interesting stuff as we change those tables into an HDFS table later in our demo. So actually, I think I'm going to let you jump in and tackle what our HDFS architecture looks like. So we're going to flip back their slide deck now. So, thanks.
Well, resolution always throws you off. So, all right. All right. So let's get back into sort of everything to do with HDFS. Right. So what's our general architecture with HDFS? Like just a refresher, I said this before. Two primary modes of how the data will land up into HDFS. One is this sort of, hey, keep writing into this huge main memory tier. I can do buffering. Take the batches of data, keep on streaming into Hadoop as fast as you can. Right? It's all about extreme write throughput and write scalability, fast streaming writes. The second is a sort of random read write, which is the operational database and a huge chunk of data in HDFS. But the other interesting point is that now whenever we write into Hadoop, in both these modes, when we create, and I'll show you later on, when we manifest these records inside Hadoop, we will actually timestamp them, right? So you can essentially, I don't want to call it a time series database, you can essentially walk through records and see when certain events and operations happen, and then do some sort of processing on it, right? So that's an interesting point. All right, so what does it look like syntax-wise? Well, it looks like any other database, I suppose. So much like how if you're used to like Oracle, you create a table space, right? Every time you're dealing with anything in a disk repository, you create a table space. Much like that, we have this notion of a disk store in GemFire, SQLfire, and so would be the case with GemFire XD. You create an HDFS store. You simply point to the name node. In the future, we'll have potentially multiple name nodes. You identify your root directory where all your data is going to manifest. And there are a few other optional sort of parameters, but they all have sensible defaults like batch size and batch interval. Essentially what that says is, hey, keep building these batches, but if either of these two thresholds are breached, take that batch and stream it into Hadoop, right? So this is all about just streaming writes, right? And the last thing is really saying, hey, anytime you're batching and queuing stuff, well, if your cluster goes down, I can't lose my data. So you want to identify saying, hey, should the queue be persistent? Should the queue simply be replicated in memory? So all these options to really, based on a comfort level of, what you can tolerate in terms of loss and reliability. There are a whole bunch of options there, right? But anyway, so that's typically something that an administrator would do, right? Set up these so-called, HDFS stores. And then as a developer, all you would end up doing is, hey, so you simply create a table, and you see this additional sort of syntactical sugar that we have saying, hey, it's persistent, and the HDFS store is a named HDFS store, and by just simply tagging write only, you're basically saying, hey, keep on streaming. I'm only going to write into this thing. I'm not going to read back. So the read write is as simple as you just remove that write only tag, and it literally becomes a read write table, which basically says, hey, what should I store here? What could go into HDFS? And if I don't have something in memory, I'll automatically fault that stuff in from HDFS, right? So here is the write path. So the way, like Anthony was saying, anytime you're looking at stuff in our in-memory tier, whenever you partition stuff, we essentially logically, or rather physically, we create n number of buckets. It's much like, what a hash map looks like. I said these buckets are all distributed and fault tolerant. And the clients essentially at the JDBC level, the driver is intelligent enough to grab the bucket level metadata directly into the client, such that when you do an insert, it's able to just directly route that insert to the right partition, right? So it basically looks at a single hop. As to the extent possible, it avoids unnecessary centralized servers to hop to the right partition. It directly hops to the right partition. So there it will probably, if it's configured to be highly available, there will at least be one sort of backup guy. So you write it in the primary, you route in parallel to all the backups, right? And then each of these nodes is going to write to its own local queue, right? So in some sense, this architecture is all somewhat similar to what you would see in HBase with the mem store and all that. But like I said before, there is a significant more emphasis in our sort of thinking in what is in memory and indexing and transactions and all that sort of stuff, right? So that it's much more close to what people are used to with databases. And then on the back end, as you keep on building up your buffers, it's essentially like a rolling buffer, right? So you fill up a buffer, and depending on those attributes as showing before, you take these buffers and start using the DFS client and route it to the data node. And I guess guys know that anytime I create a file in Hadoop, I'd always talk to the name node, who is the master for all the metadata. He basically says, here's a block in create, and here's a data node you can go and talk to. So, but once I have that file open, I can just keep on streaming directly to the data node, right? And one of the things we do is every time for each bucket, we essentially land up having, I mean, this is sort of the directory structure inside HDFS. You really want to make sure that your architecture is such that if you landed up essentially running your Hadoop cluster alongside this in-memory cluster, essentially have the same set of machines in which you're running this. To the extent possible, you want to essentially get co-locality, right? Your data node and where you write to disk, to an extent possible, should be the same guy who's essentially storing it in memory inside, if you made GemFire XD. And that is enabled by essentially having this architecture that says, hey, each bucket essentially gets its own subfolder. So I keep writing to that, and the Hadoop DFS client will try to essentially localize that, assuming there is space and stuff like that on that node. And the other nice thing is that the moment we try to do rebalancing, essentially you added more capacity in the in-memory tier, you really again want relatively quickly for those buckets, the data that's manifested inside HDFS, to also migrate to the right nodes, so that again you continue to maintain the locality of reference, right? Like I said before, all records that are sort of making its way into Hadoop are timestamped, so they can do an incremental map-reduce. All right, so the read-write thing is a lot more complex. You can't just buffer and say, hey, keep writing. So those of you know, I mean, the design is all sort of came from what Google did with, Big Table, which is the same thing in, Cassandra, same thing in HBase. I mean, our thing is everybody has a variant, right? But the core of it, it's a log-structured merge tree. It's really, I mean, how many of you know log-structured merge trees? So the idea here is it's very similar to the persistence architecture we have natively in sort of GemFire, right? Which is a design, if you look at traditional databases, it's all about B+ trees, right? And nothing beats a B+ tree in some sense. Somebody could say, there are other trees like a fractal tree, but a B+ tree is all about saying, hey, if I want to do a lot of queries and I want to get to those blocks with the least number of seeks, it's really designed really well. But it suffers a lot when it comes to a write-heavy application. So in general, we are biased by saying that the data structure that we want to manage on disk, essentially in HDFS, needs to be such that it's highly optimized for writes. And that's where sort of this log-structured merge tree comes. And what the idea, general principle is that, hey, you keep buffering as much as possible in memory, right? I mean, all these writes and updates and deletes are happening, buffer it in memory, sort it, right? And then you take those sorted blocks and just dump it as a new file, right? Now, you're not seeking anything anywhere. You're just dumping it directly, and so you can stream it directly to disk. And while you're streaming it in, you're writing sort of blocks of data, right? As you write a few blocks of, real data records, you sort of interleave those in with these indexing blocks, right? So you've written all your blocks out. In the end, you dump essentially another big sort of indexing block that essentially allows you to point to these, these pages, if you may. And the whole idea being saying that, hey, if I were to look for any record, I can very quickly look and find the right block that actually has the record and bring it in, right? And so the way you have to do it is, I mean, there are a variety of other things to do. I mean, we add a Bloom filter on top. A Bloom filter is a data structure that basically says, hey, what is the most quick way to test whether, given a key, does this sorted file actually have the key or not? I mean, it basically can give you false positives, but never a false negative kind of thing, right? So you can essentially find your records rather quickly. Now, as you can imagine, if I'm in a system which is constantly doing updates and delete operations, right, then you're constantly building up these files, because these files are immutable files inside Hadoop. You're just building up all these records and records and records. So how do you can't keep on doing that. You have to compact. So there's a compaction scheme that's built in. I don't know whether I have oh, there you go. So I'll just skip and come back, I suppose. The compaction scheme is a tiered compaction model. And the whole idea is to basically say, the way it works is, as these changes keep coming in, we keep creating these buffers get full, it's sorted, you dump as new files. Each essentially bucket, each node is doing it in parallel. When you have some capacity filled up, you do what is called as a minor compaction. The minor compaction is nothing but taking these files and creating one single file, right? So if it so happens that by the time I reach the compaction cycle, all the records I've created have been deleted, well, there is nothing to do. You can just throw away these files, right? So that's the beauty of it. So if you have these algorithms that are loading a bunch, doing, inserts, and then you run your batch cycle or whatever, and then toss it away, it's a great way to do this, right? You can just quickly just sort of remove your files and you're done, right? Nothing more to be done. But anyway, so I mean, if you land up doing a minor compaction, it's again sorts out these records, dumps it back in. And then at the end, there is a thing called a major compaction, which basically takes, if the minor compacted files reach a certain capacity, you do a major compaction, which basically says, here is one file for that bucket that actually has all the records in it, as if it's a single file, right? So that's one of these trade-offs. I mean, how much do you spend on doing compaction? Because compactions really balance out the read-write throughput, right? Because one of the challenges with compaction is that you have to keep on reading the records back in so you can resort it and write the new file. So if you're doing too much of that, it can result in it's a pretty common problem these days, that you can result in an I/O storm inside the Hadoop cluster, right? So your cluster is just busy just trying to do compaction all the time. But the nice thing here is that you can control when do you want to do compaction cycles. Maybe do it at the end of the day. You decide depending on how much disk capacity you're willing to sort of tolerate, right? Okay, let me go back here. So the read path, it's pretty straightforward. I mean, so one of the things we try to do is, given enough memory, we try to keep all these indexing information, right? All these indexing blocks, the Bloom filters, all that to an extent possible, all in memory, right? So that, I mean, if I have a miss inside the in-memory tier, I look up inside any of these rolling buffers, if you may, these queues that are building up. If you can't get it there, you go look up the block cache to say, hey, do I have enough meta information to say this is exactly the block I need to read to get the record out again, right? So in theory, if all the metadata is in memory, you can, in some sense, get an O1 lookup even on a miss, right? And so essentially, a single disk seek can essentially fetch you the record, right? And then the other nice thing is that, given that we try to localize on the data node, you can do a short circuit read. I mean, a short circuit thing is an option now in the DFS client, right? So essentially, it skips the data node to directly go to those files and fetch the records back in. Again, you can avoid unnecessary copying, right? All right. So the final quick slide on sort of this architecture is this closed loop with an analytics, which is the idea is that, hey, I'm writing all this stuff. It's all emerging in Hadoop. It's recorded in time order now, right? I mean, so the time order thing is, if I do want the time series thing, you have to be, you have to do compaction in a very controlled manner. But let's say turn off compaction, well, you literally have all these records that are literally changes as it happened over time. So the idea here is that we would essentially, we'll get into that in a second. We support this notion of, an input and output format. I mean, how many of you know input-output format inside Hadoop? Okay, a couple of you know. I mean, so the idea, so if you look at Hadoop in general, it's got a nice pluggable mechanism that says, hey, the data is coming from all sorts of sources. It's in all sorts of formats. I mean, how do I do a map-reduce so the mapper gets a record where I want to transform it before the mapper sees it, right? How do I run a Hive job where the Hive, when it's looking at the record, can be flat, can look at a record as if it's just a flat record that can consume for SQL, right? So essentially, it has this notion of when I submit a job, let's say in MapReduce, you can say, hey, here is the input-output format I want you to use as a plug-in mechanism. So when you write your map in your reduce program, it's, you have abstracted away. But that's the idea, saying that even though my record that I'm formatting is, like I said, it's mixed in with indexing information, there's Bloom filters, all that sort of stuff. I can essentially take that record inside Hadoop, reformat it, and give it to you in a form that you can consume now without actually having to go through that in-memory tier, right? So I can do analytics. So we have this input format. Likewise, we have a notion of an output format. If you plug that in, when you write your reducer is producing some output, if your output format is plugged in, that data will automatically emerge onto the in-memory tier, right? So the idea here is to say, hey, how do I use HDFS and the mechanisms in HDFS as a glue to create a closed loop system between what happens in sort of your online real-time world and what happens in sort of this analytical world and a batch-centric world, and I can get essentially much more real-time information flowing all the way back in, right? Okay, so let's just quickly look at the HDFS extension, I suppose. Hopefully you can.
Yeah,
the
definitely.
resolution.
That's pretty cool stuff.
Right.
So this time in our demo, we're now running PivotalHD, and that's where we're going to store our data. OK, so we're going to take those same tables, and let's take a look at that schema. All right. So here's a table. We are adding that HDFS store keyword so that we are now flowing it into HDFS. Our HDFS stores, we're calling it airlines. We give it the name node address, where we're storing it, and how often we want to dump that data out to HDFS. So here, just for demo purposes, we're doing it every 5 seconds, which is pretty quick. It'll result in really small files. Typically, you want larger files so you don't have to do as much compaction. OK, so we created a little shell script here that's going to go off and do a bunch of stuff and basically throw that all into HDFS. So let's just kick that off. All right, so it's creating our schema, and now we're going to go off and throw a bunch of data in there. And as that's running, we're going to go back and take a look. If you've ever done any Hadoop work, there's this handy little web page that comes with it that lets you browse the file system. So we're storing that in our SQLFire directory. You can see 2 table names here, flight availability, flight history. Let's take a look. As Jags showed before, we're storing the data in buckets. Each directory here has, matches to one of the buckets that we're hosting that data in. And then I can look at the actual files themselves. So these are our log structured merge tree data that we're storing. If you really wanted to look at it, you could take a look, but I wouldn't recommend trying to read it. This is where you use an input formatter. Anyway, so that's where our data lands up. Pretty cool. OK. So I hope you realized that was really simple. All we had to do was add a keyword, and now our data is both in memory and being written out to HDFS. So not much that you have to do as a user, but under the covers, we can manage that for you. There's a lot more options you can do with that HDFS store. You can identify how often you want to do compaction. You can make it a persistent queue, all sorts of fun stuff. So we did our demo. If you're wanting to, actually, before we go on, I wanted to actually go back and show you a few other things. So we got our data in HDFS. Let's actually run some. Let's run a query that's a little more complicated. It's got a join. It's got an order by condition. You're gonna, it's got to do a few things. So we're going to go ahead and connect up, and then I'm going to paste that in and let it run. So you can see it went out to HDFS. It grabbed all the data. It's kind of hard to see exactly what that data is, but it's airline history data. So
so when you input it, it's not storing it in memory like SQLFire normally would. It's putting it in the store, or
yeah, that's a great question, and I'm glad you brought that up, because that's really I think the key to this whole thing is when we insert data. When you say insert, into whatever table it is, the data is going both into the operational data store in memory inside our GemFire XD, and we're also flowing that data into HDFS. So you're probably thinking, well, my in-memory system is sized at 1 terabyte, but my actual data is 100 terabytes. So how do we actually manage that? There's different ways to think about it, but one way we want to, we're focused on in-memory, real-time, low latency results, very predictable results. So we want the actual data stored in the in-memory tier to be very predictable as well. So as part of creating that table, you can specify eviction criteria that says, maybe I only want to keep the last 5 minutes of data in memory because that's all I need to have around in my online tier. And because the speed of my incoming data it's streaming in so fast that it'll overwhelm memory if I try to keep more than that. So you can evict, based on time criteria. You can say there's a certain class of data, like a customer classification or some other class of service that you want to report on. Basically, any SQL condition you can identify that says, if it doesn't meet this, we're going to evict it out of memory. And we'll still be able to fetch it from HDFS, but you won't have the same high performance in memory results. So the other side of that is, so we control what's in memory, but then we also allow you to control where your queries go against. So you can, we have some query hints that let you say, I only want to run this query against the data in memory because I know it's already there based upon my eviction criteria. And that's going to be super fast. There's other query hints that you go out to allow your query to expand out and fetch data from HDFS. And depending upon if you're doing like a primary key query where you know all the IDs you want to fetch back, we can do that, like Jags said, with pretty fast performance because we can use our Bloom filters to prune down the set of files we read from. We have indexes inside those files in HDFS that let us jump directly to the block that we need to read. And we can read that block back and find that key pretty quickly. There's other types of queries that we're still looking at, but as you get further into the realm of reading billions of rows, that's where you want to think about, do I really want to fetch all that data back into my online system, and what's that going to do for my performance? So the key point here is to think about, how can I have high performance even when I have a billion rows of data, and kind of design that ahead of time. OK. So now we're going to take a look more at the map-reduce side of the world. What do I do once I've gotten my data in, it's landed in HDFS, how do I read it? So if you've heard those talks this morning, they talked about map-reduce and how you read the data. So the first step to kind of reset here is Hadoop provides a nice plugin architecture using input format and output format that lets us read arbitrary kinds of data or write arbitrary kinds of data. You don't really have to worry about that as the application programmer because the person who wrote that data is going to give it to you. And in this case, GemFire XD is going to have that for you. But to kind of reset how MapReduce works, we've got a mapper. It's going to transform the data in some way. So every time you run a MapReduce job, it's going to split that data up into a set of keys and values that are on the local data node and send that into your mapper one at a time. So inside your mapper, you transform the data. You may filter it, validate it, correlate it with other information, and spit out some intermediate results. Hadoop will then shuffle that around and send all the values for a given key to a reducer. So the reducer's job is to take those values and spit out some sort of aggregate. And it sends that aggregate value to your output formatter. So as I mentioned, for GemFire XD, we provide an input formatter that knows how to read the rows of data that are written using either our streaming model with write-only data or the read-write model for our log-structured merge trees. So it reads the input formatter, and one row at a time, we send that through the mapper. On the output side, the reducer data is sent through our output formatter and inserted into some table that you want it to go into using insert statements just through standard JDBC calls. So how does that look like in practice? Here's a sample mapper job. I'm not using the standard word count thing, but it looks like that in many ways. In that, what's happening here is that you've written a mapper that we want to use for counting up airports. The end result of this is going to be what's the busiest airport. So to start out with, in the mapper, we are given a row of data. That row of data came originally from an insert statement that was sent into GemFire XD. From that row, we can pull out a result set, and using standard JDBC APIs, which I'm sure you've seen before, we can extract column information. And in this case, we're looking at the origination airport and the destination airport and firing up a counter against that. You can see, associated with each mapper is a bunch of job configuration data in Hadoop. In our case, you need to specify where the data is located in the home dir. You have to specify an input table, which is flight history. And then you specify the input formatter that lets Hadoop know that this data is coming from GemFire XD. Does that make sense so far? Any questions? OK. So if you heard another talk this morning, they were talking about Spring Hadoop. And the whole thing about Spring Hadoop is it makes all that boilerplate code that you have to write for the driver portion of MapReduce. It simplifies the job configuration. So here's another way to do it. It's a lot easier. If you're going to do it a lot, I would suggest taking a look at it. OK, so back to our example. We want to calculate the busiest airport. So the first thing we did was we captured the origination and destination airports. And I kind of skipped a reducer here, but there's a reducer that goes off, and calculates a sum over those different airports. So it figures out which one, if it sums up the usage of each airport. What this reducer is going to do is it chains on to the previous one and calculates a maximum. So it's a simple loop through all the values, figure out which is the biggest one. And once we've captured that, we're going to create a simple Java POJO object and send it to the output collector. And again, you can see that job configuration has to be, we have to specify JDBC URL, the output schema, the output table name. In this case, we're going to send that to the busy airport table. And we set the output format to the GemFire XD output formatter. OK. So once we've done that, what's the magic? Where does the data go? Under the covers, we take a look at that. The output formatter grabs that busy airport model object and matches up the table you've given with this POJO. And using the column names, we can build up these put statements that let us use JDBC to shove that data back into your online system. So kind of to reset here, what we've done is an insert statement that started out with your client, went over JDBC into GemFire XD, that got sent into HDFS. We ran a MapReduce job on it, and then we took the results of that MapReduce job and sent it back into GemFire XD. So with that closed loop, what we can do is we can take those MapReduce jobs and make them immediately available to your online apps so that you don't have to wait 12 hours or whatever it is to do this huge load of data from your batch HDFS results, batch those into some online system. We can create this closed loop flow. All right. So given that set of code we've looked at, I'm just going to run a quick MapReduce demo that shows how that works in real life. So we've already written it, and there's this little shell script with a bunch of options that I don't have to type in. We're going to go run this. OK. So let's fire this thing up. OK, so now we're kicking that job off. It's going to run that first mapper that collects all the airport information, then a reducer that sums up all of our counts, and then another reducer that's going to go off and find the maximum. And at the end of it, we should find some information back in our busy airport table. So let's start up SQLFire. We're going to connect. We're going to do select star from busy airport. So congratulations, Miami won the day, I guess. So, question? That's a good question. We called it the same name. There's no necessary, it's not necessary that it's the same name. We could call it any table you want. And in fact, there's a lot of JDBC tools or frameworks out there that you may want to use, whether from Spring or other places, that you could decide how you want to insert that data yourself. Yeah, good question. Yep, so there's our create table busy airports. That's what it looks like. So we've got that table existing in our schema, and then once the reducer is finished, it's going to batch up these statements and then commit it once the data is all there.
Yeah, so one of the interesting patterns is really, you're just loading data from all sorts of sources directly into Hadoop, maybe just fluming into Hadoop. And we see this common request saying, hey, I just want to run a whole bunch of MapReduce or Hive or whatever. And as I'm emitting results, I just want those emitted models to just appear in my online operational tier. Right? So in fact, his, what did he call it, the table, the busy airports table itself could also be a Hadoop mark table. In other words, the tasks are running, the tasks are emitting data, it's going into sort of this in-memory tier, putting it on there, and through the GemFire XD's mechanism, making its way back into Hadoop, right? So it's also common, but pros and cons to any of these approaches. So.
Yeah. So while you're running PivotalHD, they have their own command center. You can take a look at the results, name node contention. It's kind of hard to see with this resolution. The different MapReduce jobs that are running. I think there's a default one that comes with Apache Hadoop that you can go in and look at your MapReduce job itself and see what the results are, how much data it had to consume, how long it took, all that sort of. I'm trying to figure out if my job worked or not kind of info. So. Any more questions? We've got more stuff to go over, but I want to make sure we cover this. Go ahead.
Quick question. So the data stored, the format stored in the HDFS, does that have to somehow optimize to support the way it will be correlated later, or?
Yeah, that's a good point. We definitely optimize it for read operations. So we use the log structured merge tree approach. So every file contains a Bloom filter, which is a space efficient way to decide if a key exists in a file or not. And it may lie to us, but it won't tell us it's not there if it really is. The other thing is every file has a primary key index that lets us find exactly where a block is, where a key exists, which block in that file the key lives in. So we can do pretty fast access to that. I don't know if that helps out. Okay, there's another question up here.
So if I understood correctly, it makes sense to co-locate the data nodes as a local store when you use the HDFS store for creating a table from GemFire XD, for instance. So how does it have, what is the situation when a WAN replication comes into the equation? So GemFire XD by default does the active-active WAN replication.
Right.
So how do you tackle at the Hadoop level?
So no, oh sorry, yeah. So the question is, in GemFire and SQLFire, we have a notion of a WAN gateway. So you can essentially take the data in one cluster and replicate it to other data centers. So the question is, how does it play into sort of from a Hadoop perspective when the data is in Hadoop? So the simple answer is, if all the data you're inserting into Hadoop is essentially coming in through the SQLFire tier, then as long as your tables are configured to replicate to the WAN, all that stuff is going to go over the WAN too, right? So you can essentially do this thing where a table can be a memory resident table. That data can go over WAN to other clusters, can go essentially get queued, get into HDFS, can get queued, get into an RDB. It's up to you So you can essentially configure all of that. It's just a configuration option. Yeah.
Aren't what you're saying, you've just solved the problem of having site redundancy in your HDFS. Like, you're asking about your HDFS underneath, and I don't think it does site redundancy out of the box or anything, but using GemFire, you could basically write to two different HDFSs and two different sites. And
That's true. That's true. I mean, only for the data that's coming in through sort of GemFire XD, right?
well, why wouldn't you
Yeah.
go through there?
Yeah. So, you know, as long as you can go through it, yeah.
You gotta put your sales hat on.
That's true. Yeah.
One quick question also. So, I mean, does Hawk, all this out of the context of this, fit in any way in this?
Oh, absolutely. We didn't
Yeah.
cover that. I mean, there's quite a few actually slides which we didn't talk about yet. So the overall sort of, you know, pivotals, if you may, the data fabric picture as a vision that we're painting is that we're trying to say, hey, HDFS in some sense is a substrate that all of us will depend on, right? So you have this online application, writing stuff is emerging onto HDFS, and if you look at the Hawk design, they have this thing called, you know, the pivotal, what is it called, PXF, the pivotal extension framework. Thank you. So we are going to have a PXF driver for GemFire XD, so that you can run a query, a deep scale query, if you may, on top of Hawk, and we'll be able to sort of fetch it as if it's an external table directly from the data that's been manifested from here. Likewise, when you write back output to a table, that table could simply be a table inside GemFire XD, and it'll emerge into the in-memory tier also. So you'll have that, absolutely.
Play the role of the cache layer in the conventional databases in the conventional model.
I'm sorry, can you repeat the question?
That's maybe I misunderstood, but in the case of Hawk, so the GemFire would basically play the role of the cache, which would actually mediate the interaction between the HDFS and
No, not true, not true. Hawk.
next to the
Right. So the question is, you know, is GemFire XD playing sort of an intermediate sort of caching kind of role between Hawk and what's happening in HDFS? The answer is actually a no. Hawk will natively try to write to HDFS for the tables that it's natively managing in HDFS. But the idea here is to basically say, hey, what is the connection, and how is it that if Hawk is producing models, output models, how is it that those models will flow back into my online real-time, quote-unquote, real-time applications very quickly, right? The traditional way of doing an MPP database is, hey, you write to your operation, you write to your Oracle, your Sybase, what have you, and then, you know, output becomes visible to your online. So we are saying, hey, this is now a much more of a real-time, a very native way to sort of get that data back into your online. So the idea is that, hey, the output stuff kind of comes into HDFS, if you mean, inside the map-reduce yarn-like layer, and from there it'll shoot across to the in-memory tier. That's the idea. Yeah.
Go ahead.
I have a follow-up question about the read access. So if I remember correctly, in your source code, there is a line in the mapper kind of like read for each row and doing something. So I was wondering, in this case, we are trying to find the business error for given the current date. So the logic is so that it will go through the HDFS to read all the rows.
No, that's a great question, yeah.
And to pick up the sum. How that works?
The quick answer is a no. I mean, we didn't cover all this. I mean, there's a lot of flexibility, right? So when you submit a job, you can essentially specify the time frame also, right? Given that, you know, as we are manifesting these files in HDFS, these are all, like I said before, time-stamped. I mean, in fact, I mean, if you show the format of the files actually have a notion of time right there. So, you know, when you submit a job, you could say, hey, within the last hour, do this. Look for the records within the last hour. Now, it's not going to be that precise, you know, granularity that exactly an hour ago, but roughly it's going to target that data set because of this manifestation of these files. So we didn't cover all this, but yes, absolutely. That flexibility of saying, can I do an incremental map-reduce? Absolutely lies there.
Yeah, sometimes you want, you know, an incremental update. Other times you want to go over your full data set. Go ahead in the back.
Sorry, watching the example there, you know that in the map-reduce space there are all these patterns, for example, map side joins and stuff like this, where the presumption assumes that you
Yeah. Yes, absolutely. I mean, nothing preventing you from saying your mapper and reducer programs cannot connect directly into GemFire XE. Let me show you one interesting. I mean, we didn't really cover all this. I mean, one of the big things that we support, which I think is a much more interesting pattern than honestly MapReduce, is we essentially support this notion of you can run a parallel arbitrary function, arbitrary piece of Java code as a procedure in a highly parallelized manner inside that in-memory grid itself, right? So I expect a lot of these kinds of things to say, load this data and you can parallelly run a procedure essentially, right? I mean, ironically, I mean, if you looked at that example, which is really like a top-end example, I mean, you can do all this 100 lines of MapReduce, or you can just write one single SQL statement and you're done, right? So, I mean, so it's, but yeah, I mean, there is this notion of saying I can run, I mean, if, this slide is sort of supposed to show that, where if you look at traditional MapReduce, it's all about, I run my mappers, the mappers are emitting records, those records are getting shuffled. While they're getting shuffled, they're making its way back into disk. There is tremendous amount of serialization, copying, moving over the network involved. Then the reducers are picking it up, again writing it back to disk. Well, shoot, why do you want to do all this when you can literally say, take my input data set, queue it in batches, send these micro batches into sort of what lies in memory. So essentially spread the data that you're dependent on in memory and just simply invoke procedures on it. And when they're producing an intermediate sets, these intermediate sets are also in memory. And then the final, potentially the end aggregated result makes its way back into disk, right? So we have this notion of just, what is called as parallel procedures. I mean, I'm not going to go through it now, but so that's another sort of alternative approach you can do. So likewise in HBase, you have this notion of, what they call as a co-processor. So where you can run sort of, if you may, procedure code inside your HBase cluster. Yeah.
How does GemFire find out about files that came into Hadoop from another angle? Right? So we want to create a table for customers, but customers are already in the.
Yeah, it doesn't. Not yet.
You can run a MapReduce job.
Yeah,
right?
you'll have to run a map. For everything, there's an answer. Yeah, run a MapReduce job, right? Yeah, so you'll have to essentially, you'll have to unfortunately feed. Because the way we store it is, right now these records are not like, oh, just store it as text records. I mean, we want to keep it very optimized, right? So the records are in fact binary formatted. But what we do is we are keeping and retaining all your data dictionary elements inside Hadoop also, right? And that's the trick. Keep that data dictionary absolutely alive. So when that task guy runs, the task tracker is immediately saying, well, let me create almost like a proxy GemFire database right there, and now I can feed you the rows because I have the metadata that I need to give you the rows back. That's the idea. So at some point in the future, we might support a very, other formats like Parquet and other formats, obviously Avro and stuff like that. Correct, absolutely. So if you want that stuff, I mean, of course, you can always write to an output formatter that has nothing to do with GemFire XD. I mean, but yeah, I mean, if you use the output format in GemFire XD, boom, it's going to materialize inside that main memory tier. Yeah.
So the metadata that you're talking about is essentially the data dictionary.
Yeah.
Essentially is the output format that is dictating.
Yeah, the output format is looking at that, that data dictionary information to know which table should I write this information back into, right? Yeah, pretty straightforward stuff.
Comment over here.
No, I was going to say the same thing. You guys are laughing about how it's like, no, it's a perfect batch load model, I think for business intelligence or something like that.
Right.
Heavy batches just use the output writer you've already written. Write a large bat files into HDF, write a Hadoop, and then just turn right around and MapReduce and massively build out a bunch of tables that they need CSVs.
Sure.
Right. Yeah, cool. Yeah, thanks. All right.
Anything else?
Anything else?
You can catch us outside or somewhere else, but thanks for your attention today. Appreciate it.
Thanks, guys.